Holy Father, we thank you for this day, the relative quietness of this class. I just pray that the campers would have a good time and keep it down. And just help the students to learn the series things we go over today, and that you be glorified in what we do learn. In your name I pray. Amen. High schoolers. Let's see here. Yeah, make sure, just if you don't mind capturing this for me. It's all been in frame? Relatively? Very good, thanks. See, I'm currently writing up a paper on this stuff, and I need to put some examples in the paper, so I may have been working on my paper with you guys. Sorry. These kinds of examples are easy. I just started with some random differential equation in the complex algebra, and then I showed you it gives you these two different partial differential equations. Like that direction's really, really simple. What's much harder is if you could just, given a system of partial differential equations, which algebra do you choose to turn it into a differential equation over the algebra? That we don't know the answer to. That's the thing. That's still a very open question. So maybe some student in the future will solve it. Anyway, I digress. Power series, what we're at. So we're looking for power series solutions to linear ODEs. Now, we'll focus, I think, nearly exclusively on the n equals 2 case, right? So basically, the problem we're solving is something like y prime prime plus py prime plus qy, and usually equal to 0. There's really nothing stopping us. We could deal with non-homogeneous problems, but I just focus on homogeneous problems. But basically, we're trying to solve that, where p and q are, analytic, at least, functions. Now, so what does analytic mean? Basically, it means something like this. P of x can be written as a sum n equals, well, let me say k. K equals 0 to infinity of a sub k x minus x naught to the k, right? To say that the function's analytic is to say that that the power series which represents it converges to the function in a sense which I don't want to make precise. Now here we have a power series centered at x naught. Often we take x naught equal to 0. So, I'll try to work at least one problem not centered at 0. But if we understand carefully how to do things at 0, it's pretty easy to do it elsewhere. Oh man, I forgot to show you guys how to do Laplace transforms for other things than 0. You might have been, like when I first learned Laplace transforms, this is something I forgot to say yesterday. It would take me 3 seconds right now. When I first used Laplace transforms, I thought, this is a worthless method. Because what if I'm given initial conditions at some time other than 0? Like, what if I know my data at time 1? Laplace transform is no help to me, right? Because it's all set up for time 0. Well, that's just the textbook and the instructor's choice. You could easily set up Laplace transform centered at time 3. And so there's a simple change of variables you can do to convert all the formulas based at time 0 to be based at some other time. One of the problems on your third quiz will show you how that works. So I'll catch up. I used to have a linear algebra class. I think it was next to I think it was a film class, and we randomly hear like snippets of some German film or something. So this is less interesting, but sorry. So my point to you is just that we usually set x naught equal to 0, and so, but I showed you the strategy for solving this last time. Given the right conditions on p and q, that they're analytic functions, all right, what we do is we just suppose that y is the power series, and we plug it in. And then we work out conditions on the coefficients of our guess, and that will give us solutions. So the best thing I can do is just start working examples, because there's really not much. The theory we've already been exposed to is the theory which still applies. There's still going to be two linearly independent solutions which form the solution set. The question is just how do we find them? It's a little different now. let's work an example here. I'll start out real small. How about this? dy dx equal to x cubed e to the minus x squared. Let's find the first three terms. Well, let's find solution, rather, to order x to the fourth. So if we follow the method I did last time, we'd say y equals to something like a naught plus a1x plus a2x squared. And I really, it's ambiguous as I said it right now. Well, excuse me, it's not ambiguous. If I say to order x to the fourth, that indicates that we're centered at 0. Right? In other words, we're looking for what's called a Maclaurin series. Right? Anyway, so a naught x1, a3, x cubed. I'll go all the way out here to x to the fourth. Differentiate it. We have dy dx is term-by-term derivatives. a1 plus 2a2 plus 3a3x squared plus 4a4x to the third plus dot, 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 dot. Right? And this one's a little bit different. Actually, I've just violated my general setup in two different ways. First of all, we're solving a first-order differential equation, right? Second of all, this is non-homogeneous. So I'm doubly misbehaving. Hope you can forgive me. Now, the reason for this, though, mostly was just I wanted to remind you guys how we find series expansions for things briefly. So this one, what I would do here, guys, is I would leave an x cubed out front, and then I would use the known power series expansion for the exponential, right? E to the u is 1 plus u plus 1/2 u squared plus 1 over 3 factorial u cubed plus dot, 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 dot. Now, that might be fresh on your mind from the matrix exponential because it's the same series, right? So all I have to do is make a substitution. U equals minus x squared, right? So this is 1 minus x squared. And it hardly matters what's after that. I'm already to fifth order here, right? So if I'm going to equate these two things, that's more than enough. See, because if I multiply this out, this gives me x cubed minus x to the fifth plus dot, 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 dot. Right, so now I have everything I need. I can equate coefficients. What do I get? So 1x, x squared, x cubed, x to the fourth. 1 gives me what? a1 equal to 0? How about the x terms on both sides? I got a 2a2. What are the x term on the right-hand side? Keep looking for it. It's not there. X squared. Is there any x squared term? Nope, not there either. X cubed. Is there? We have a 4a4 here. And x cubed. Oh, we got a 1 over there. All right. X to the fourth. I guess well, x to the fourth. I don't. That's enough. Sorry. That's the funny thing here, right? If I asked for the solution to order 4, it turns out I only need the equations to order 3, because differential equations have this habit of intertwining, if you will, different orders, right? So even if you look at the third order equation, it might give you access to the fourth coefficient. That happens here. So this is rather boring. What do we get? We get y is equal to a1 0, a2 0, a3 0, a4 is 1/4, 1/4 x to the fourth plus dot, dot, dot. There you go. Now, this is an entirely dumb way to do this example. The reason I did it this way is just to illustrate the method, right? How should we do this example? What's the smart way to do this example? But then you'd have to integrate x cubed times e to the minus x squared. That is no bueno. That's unhappy. But your heart is in the right place. we should just integrate, right? Example 2, aka example 1, done better. but also irrelevant to the larger discussion today. So, I don't know. I mean, is it irrelevant? Not entirely. So this gives us, of course, that y is the integral of x cubed e to the minus x squared dx. And so what you do is just convert that. That's the integral of x cubed times the sum, n equals 0 to infinity, of, minus x squared to the n over n factorial dx. We can clean that up. That's the sum, n equals 0 to infinity, minus 1 to the n, x to the 2n plus 3 over n factorial, right, dx. And then the term-by-term integration theorem for power series comes into play here, right? So we can just say, okay, so that's a constant plus the sum n equals 0 to infinity, minus 1 to the n over n factorial times 2n plus 4 times x to the 2n plus 4. And there you have it. That is, I think, a better answer in some sense. It's the complete answer. It's not an approximation. That's the full, honest-to-goodness solution to this differential equation. If you put in n equals to 0, what does it produce? Oops, there's no factorial. Right, n equals 0 reproduces what we found in our term-by-term analysis. But this is a luxury, right? Being able to isolate dy dx and then integrate both sides. This doesn't usually happen. Most differential equations are not so forgiving, right? We could have something like y prime prime plus the sine of x times y prime plus 3y equals to 0. And I'll bump it up a notch here. I'm going to say y of 0 is 1 and y prime of 0 is 0. Right. Let's find the solution to order 8. Oh, I may regret that. I'm gonna fill in a blank here, and we'll decide what order we want to work it out to after we do a little bit here. How about that? Okay. So how do you do the problem like this? Well, the point here is that this is y prime prime plus, what's the power series expansion for sine? It's x minus 1/6 x cubed, right? And so forth and so on. I'm just going to go that far so that we don't get too overwhelmed with it in class. And then I got a 3y over here, yeah? But the thing is, okay, so that's what the differential equation looks like, right? So in this case, I had a coefficient which is best defined by a series, right? I need to actually expand the sine into a series in order to use our method. And this is the Maclaurin series for sine. So we let y equal to a naught plus a1x plus a2x squared plus a3x cubed plus a4x to the fourth plus da da da. That gives me y prime is a1 plus 2a2x plus 3a3x squared plus 4a4x cubed. I probably should have written this down somewhere and keep referring to it. Yeah? Oh well. Y prime prime, 2a2 plus 6a3x plus 12a4x squared. That's all we need. So what we do You take those, right? You take these, and you plug them up in here, right? Now, you got to make a decision whether or not it's actually beneficial to actually write that out, or if it's, better to just think about what happens when you write it out. In this case, for me, I think it's better to write it out. But you got to be careful. Anytime you do this, this is the usual step where a mistake is made, because whenever you're like transcribing these things, it's really easy to drop a sign, multiplication by a constant, whatever. Probably writing more than I need to here, but there we go. I've moved to non-standard board space. So anyway, all right. So there it is in all of its glory, and all we have to do is collect order by order what are the equations which we face, right? So I usually start out with the constant term. So constant. We've got 2a3. Anything else? Nothing from here. Oh, plus 3a naught. 3a naught is as low as you go. So this gives us the relation between a3 and a naught. In particular, a3 is equal to minus 2/3. Well, excuse me. What's that?
Isn't that supposed to be 2?
Oh, yes. Thank you. I was like, this is weird. I was just thinking, this is a strange pattern. Yeah, because that's a mistake. Thank you. What was I just saying about making mistakes, transcribing that? So, yeah, I can tell you I'm a prophet. Let's see here. Not as in one who speaks the truth, but as in one who foresees the future. Let's see here. The equation I wrote was a lie. All right, 2a2 plus 3a naught, yeah, equal to 0, which tells me that a2 is minus 3/2 a naught. You always want to connect higher coefficients to lower coefficients. And, aw, man. See, I'm sorry, guys. Well, this is the thing. I forgot my starting point when I was doing the calculation. You could have said that this is equal to 1 plus a2x squared. Because these. Now, you can also impose those later, right? So no harm, no foul. But the fact that the derivative is 0 could have saved me a lot of writing. Not a lot, but every time I had, like all of the, basically a1 is 0, right? So that's gone, that's gone. It's not a big savings, I suppose, right? But this is 0. This is 0, Okay. Next, x's. So coefficient of x, what do we got? We've got 6a3. And see, I would have thought I had something here, but I don't, because a1's 0. Right? And that's the only way you can get x from this product, because x cubed times stuff is order x cubed or larger. So that was our one hope from the middle term, providing something non-trivial for the x equation. It's gone in the non-trivial sense. Oh, and over here also. So check it out. A3 is 0. let's go to the x squared equation. What does it tell us? What do we learn from x squared? We get 12a4. How else can I get x squared? I can get it from x times 2a2x, right? That gives me an x squared type term. In fact, that gives me 2a2. 2a2. Any other way to get x squared from the middle term? I don't think so, right? X times x gives me an x squared, but x cubed times x cubed doesn't give me an x squared, right? I mean, then over here, what? Plus 3a2. Aha. So therefore, a4 is equal to minus 5a2 divided by 12. All right. I'll do one more. X cubed. What do we have for x cubed? I didn't write it down, but what would the next thing be here from y prime prime? This is 3 times 4. The next one's 4 times 5, which is 20a5 x cubed, right? If you think through that, we start out with 5, a5x to the 5th, differentiates to 5, a5x to the 4th. Then 5 times 4 is 20, a5 x cubed. Yeah, differentiate 2 times. So there is our 20 a5 from the y prime prime. And how else can we get x cubed? Can we get x cubed from here? Yeah, x times 3a3, right? But a3 is 0, right? Maybe I should have taken account of that. So that's gone, right? By the way, making these kinds of simplifications mid-calculation does have its danger, right? If you've made a mistake and you're thinking that it's 0, then you're propagating that mistake. If you don't impose it till the end, I mean, you know, there's benefits and there's pros and cons here to that kind of calculation. But all right, anyway, so how else can I get x cubed? How about, oh, I could in principle get x cubed times a1, but again, that's 0, so, well. But from the 3 term here, let's see here, we got 3, oh, but a3 is 0, right? All right, well, anyway, so that's 0. So apparently, a5 is what? 0, right? I'm starting to believe that if I was to keep working on this, maybe I would find that all of the odd coefficients are 0, but it's too early to conclude. It could be that the first few odd coefficients are 0, and yet the later ones are non-zero. That can happen. All kinds of things are possible. All right, so collecting our thoughts. Our solution, y equals a0 plus a1x plus a2x squared plus a3x cubed plus a4x to the 4th plus dot 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 is going to be equal to a0 plus, what was my a2? My a2 was minus 3 halves a0x squared. a3 was 0. a4 was minus 5/12 a0 x to the 4th, right? That's my a4, and so forth. So you can factor out the a0. But what was a0? I mean, I actually should have, I mean, we touched on this earlier, but I didn't really propagate that thought through the calculation yet. Yeah.
For your minus 5 over 12 term,
Uh-oh.
isn't that supposed to be multiple of a sub 2, not a0?
Oh, thank you. So minus 5 over 12, and then I should put in my a2, which was minus 3 over 2. Thank you. a0, which would have been actually, I was wondering why that was negative, negative. There are series which have negative, 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 but it's more off, like a lot of times I see plus, minus, So when I see negative, 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 it makes me wonder if I made a mistake. I'm glad you found it first. 15 over 24 a naught. That simplifies, doesn't it? That's 5 over 8 a naught. So in fact, that should have been 5/8 and a plus rather than a minus. Thank you. By the way, there you go. So the solution is 1 minus 3/2 x squared plus 5/8 x to the 4th plus dot 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 dot. This is in fact the solution, in fact, from what we've done to 5th order, right? Because we've in fact shown that the 5th coefficient is 0 as well. So the thing we don't have knowledge about yet in our solution here is the 6th power, right? So this is really to the 5th power, even though the 5th power is trivial. Depending on how you want to think about it, I suppose, but there it is. Any questions? I'll fill in my blank. I decided 5. All right, so what I've been doing up to this point, in the example from last class, in example 3, and in example 1, is just a partial calculation, right? To use power series method to find an approximation for the solution to some order, right? But we can also find complete solutions to differential equations using recursion, or just basically pattern matching for such a problem. Probably be good for me to work such a problem because it involves a slightly different skill set, although the overarching logic is much the same as what we've done so far. So let me do that. If I can find a spot. What I usually do is I usually go back and solve a problem which we have solved a different way. All right. So admittedly, if I was to ask this on a test, I always have to be very, very rigid in my instructions. Solve this using the method of power series. No credit will be awarded otherwise, right? So, because otherwise, when I write this differential equations down, you, unless you're otherwise guided, would be a fool to use power series, right? So example 4. Y prime prime plus y equals to 0. Right? You know the solution to this already. But let's derive the complete power series solution using our method. Centered at 0. All right, so what we do is we're going to say y is equal to the summation. And so the other thing I'll do if I have a problem like this in a question, I'll use language like find the complete power series solution. I might even include the phrase use sigma notation. This is sigma notation, right? So if I ask you to find the complete power series solution using sigma notation, and then you do like what we did in example 3, you're not going to get full credit. You might not get much credit at all. It kind of depends on my mood, to be honest. So let's see here. I mean, it's true. There is subjectivity in math. Let's see here. So are you saying we should bribe you? No, I'm not saying that. But I'm not saying it either. Wait a minute, no. I'm not a politician. I can't say these sort of things. N equals to 1 to infinity. So the derivative is n, an, x to the n minus 1. Notice that I rewrite the summation at 1 because, well, the 0 term is just 0, right? So we can re-index starting at 1. And y prime prime is the sum n equals 2 to infinity, n minus 1, a sub n, x to the n minus 2. So here I'm just differentiating term by term, right? By the way, guys, there's really no convincing reason to me that this shouldn't be covered in Calculus 2. What we're doing right now is completely a Calculus 2 problem. What am I using? series. I mean, that's it. That's the totality of what we're doing. We're just plugging series into a differential equation and working out conditions on it. And that's why I have taught this in calculus too at some point. It was okay. I don't know. I can't remember. I probably wouldn't do it again. If I know it's good for me, I won't do it again. But y prime, y. Okay, so now what we do is we plug it back into here. But the thing is, think ahead, think ahead. What we're going to have to do is we're going to have to add this series to that series, plugging it back in, right? But you can't add apples to oranges. Like if you try to add this series to that series directly, you're in trouble because this is x to the n, this is x to the n minus 2. All right? So what you want to do is you want to make them look the same. So what I do is introduce a new letter. Some people will use n again in a different meaning, but I just think that that's awful. So I refuse. There has to at least be one step in between for me. J equals to n minus 2, right? If I do that, then this is equal to the sum. J equals to 0, right? See, because when n equals 2, j equals 0, right? What happens when n equals infinity? What's j? It's infinity minus 2, right? I'm just kidding. We still write infinity. Okay, so infinity. As we discussed, infinity minus 2 is still infinity. All right. Tell your kids. If you have them. Maybe you're like Dr. Sprano, who sometimes is known to say, none that I know of. Which is funny if you know him, because it's absurd. But anyway. I shouldn't say that. All right, let's see here. So the n is j plus 2, right? See, if the n is equal to j plus 2, you agree? So n minus 1 is what? J plus 1. And it's a sub j plus 2, right? And that's all times x to the what? X to the j. Now I want to make what I wrote in blue look like the y. How do I change the first sum to look like the blue sum? This is really, really deep. So pay close attention to this step. See? Now it has a j. Why is this legitimate? What does a summation from n equals 0 to infinity mean? Is the n really part of the summation? Not really. It's a device we use for capturing this series, right? And so I can replace the dummy index of summation with j just the same to make them match. Right, yeah.
Now, wouldn't j be equal to two separate things? Now j is equal to...
Again, j is just a device for expressing a series. It doesn't have its independent existence. There's no j. This is a sort of philosophical point I'm trying to make here, but these are notations to indicate certain series, right? Now I've made these two series have the same format, which means that there's a theorem that says I can add them by adding their coefficients. That's, yeah. But what you're saying is something that someone always thinks, and sometimes, like last time I taught differential equations, at one point somebody was like, in the middle, he's like, but you can't do that, because you already made j this. And up here you're saying j is equal to n. J can't be n and be n minus 2. It's neither. It's a notation for expressing a series. You can't solve for j. I don't know how to get this point across. At some point we pay a price for not developing enough theory, and that's the kind of question that comes from that. But anyway, put these two things together. Y prime prime plus y equals to 0, so we're trying to solve, right? So what that gives us then is the sum, j equals 0 to infinity. And now I can add these series because they have matching x to the j's, right? So like the y prime prime gives me the exciting stuff. J plus 2 j plus 1, a sub j plus 2, and then the y gives me what? It's kind of, yeah, just that. So plus a sub j, all times x sub j equal to 0. So what we're saying is that this power series, formed by the coefficients and some numbers, has to be 0, right? The only way that that can be 0 is if it's 0 order by order by order by order by order. So it has to be order it when j equals 0, when j equals to 1, when j equals to 2, when j equals to 3. And so to understand that, we have to start writing it out. But I'll do one more sort of meta step, if you will. So what we get then is that, so this says that a sub j plus 2, a sub j plus 2 times j plus 2 times j plus 1 plus a sub j equals to 0. Now, again, j is not sacrosanct. It is just a notation to express a relation between the coefficients of the series. I don't like writing j a bunch of times. At this point, I will change back to n because it's easier for me to write. So this, in other words, says that a sub n plus 2 is equal to minus a sub n over n plus 2 times n plus 1. I mean, there are other notational paths here, guys. You could have done one more step past my blue step. You could have made a red step, right? You could have made a red step, which was that this is really the same as the sum n equals 0 to infinity of n plus 2, n plus 1, a sub n plus 2, x to the n. And then you could have combined that directly with my original y and got to the recursion relation right here just the same. I mean, however you want to get there, there's a lot of different paths you could take here in terms of the notation. But one or the other, you should be led to this relation here. And so we can start looking at things. What does this say? This says there's a connection between n and n plus 2, right? So we can kind of see, looking ahead, that all of the odd coefficients are going to be connected and all the even coefficients are going to be connected. So I'll start out with the even. Even, basically, n equals 2k. For k equals to 0, 1, 2, and so forth. These are the even ones, right? So a sub 2, for example, is minus a sub naught over what? 2 times 1. A sub 4 is minus a sub 2 over 4 times 3. But that's minus 1 times minus 1 times a sub naught over 4 times 3 times 2 times 1. A sub 6 minus a sub 4 over 6 times 5, which is minus 1 times minus 1 times minus 1 times a sub naught over 6 times 5 times 4 times 3 times 2 times 1. So, you know, keeping track of things here, we have n equals to 2k. This is my y. K equals to 1. Yeah. K equals to 2. K equals to 3. Right? So can you see the pattern? I guess if we were good mathematicians, we'd prove this by induction or something, you know. But this is not that kind of class, so we just try to find a pattern and then claim it. Right? So a sub 2k is what? It's going minus, plus, minus, plus, minus, plus. There's an alternation to the sign of the coefficient, right? How do you get that in terms of k? Yeah, exactly. And let's see here, what's this down? What's in the denominator? This is 6 factorial, that's 4 factorial, that's 2 factorial. In each case, it's 2k factorial. Now we study the odd coefficients. What happens with the odd coefficients? It's almost the same, right? What's the generic odd coefficient look like? N equals 2, let's say 2k plus 1, right? For k equals to 0, 1, so forth and so on. So let's see here. N equals to 2k plus 1 for k equals to 0, 1, 2, gives odd n. So let's see here, keeping with my organization, I'll start with k equals to 1, then I'll do k equals to 2, then I'll do k equals to 3. K equals to 1, I've got a sub 2 plus 1, which is 3. Again, going back to here, minus a1 divided by 3 times 2. A sub 5 is minus a sub 3 over 5 times 4, which is minus 1 times minus 1 a sub 1 over 5 times 4 times 3 times 2 times 1, right? I mean, I'm not sure how much writing you need to do here before you see the pattern. Probably not as much as I'm doing. I mean, you probably would see it beforehand. That's going to be 7 factorial, right? So you can, the pattern appears, right? What's the pattern? A sub 2k plus 1 equal to what? I think you guys can see it, right? It's minus 1 to the k divided by what? Divided by 2k plus 1 factorial. Yeah. And so we put everything together, right? Hence, y is equal to, a sub naught times the sum k equals 0 to infinity, minus 1 to the k over 2k factorial, x to the power 2k, plus a1, sum k equals 0 to infinity, minus 1 to the k over 2k plus 1, factorial x to the power 2k plus 1. And there you go. That's the complete series solution to this differential equation. In fact, we could use this to define sine and cosine if we were so inclined. I mean, you could define sine and cosine by these series and prove properties of them as a consequence. If you know the analysis, the term-by-term differentiation theory for series, it's not hard to prove that the derivative of the coefficient of the a1 is the coefficient of the a naught. And you can go on and prove adding angles formulas for these series. You can define pi in terms of, you can do all kinds of stuff with these series without right triangle trigonometry whatsoever. Yeah.
When you're coming up with your A2, 3, 4, or whatever, up to 7, how do you go from the left side of the equal sign to the right with the negative ones and all that? I'm not understanding what's happening with that process.
Oh, I'm plugging in the step above. So A3 is this, so I'm taking this, and I'm plugging it into A3, which is giving me this piece of it. And the 1 is just for free. And then the next time I plug in, I replace, down here I've got A5, right? So I take all of this and I shove it into the A5, which gives me, it's the same thing I did in the even case. Yeah. All right. Give me a second here. Let me look up an interesting problem, otherwise I'll make up something. We've gotten lucky so far. Typically when I make up series problems, bad things happen. So I have a tendency to say, oh, that's not going to be interesting enough. Let me make it harder. But then the devil's in the details, right? So let's see here. Where's that thing gone to? So we're back in chapter 4 of my notes. Sometimes when I teach this course, I teach series right after the first test. I mean, logically, you could do Laplace transforms anytime, really. You can do systems of differential equations kind of anytime, right? I mean, there's a certain disconnectedness from these topics, and yet you do have this sense of deja vu, don't you, as we do algebra? Like you see the characteristic equation coming up in the systems problems. You see it in the Laplace problems. You see it in the nth order problems. It's everywhere. I mean, there are certain parts of the Laplace transform experience which are uniquely that, right? I mean, there's certain weirdity, if you allow me a technical term. All right. Yeah, that's good. Here, we'll work out a nastier one. Maybe it'd be good for me to do just a different. Let me not do that. Here's what we're gonna do. I'm gonna put one up. Which was examples. This. Actually, are we done with this? I think we're done with this. So let me start over here. I shouldn't have done that. I gotta use that. Dang it. So we'll still keep it relatively simple here, but we'll do y prime prime plus x cubed y equals to 0. And I want us to derive the complete power series solution centered at 0. I'm going to take a 10-minute break. Right, we'll start again at noon. You guys take the break you want, and if you want to, you can work on this ahead of me and see if you agree. See if you actually understand what we're doing, right? So I should be back at noon and we'll start again. Yeah, thanks.